Awesome. All right. Well, hello, everybody. Thanks so much for taking the time to be with me today. My name is Zachary Proser, or Zack, and I'm a developer advocate at Pinecone. So today's talk is going to be what is a vector database? And I'm very excited to be talking with all of you about what is a vector database. And then I'll also share that my background is an application developer, and I've done front-end, back-end stuff, open source development. I've done a ton of infrastructure stuff. And so this is all interesting for me because I'm coming to Pinecone now 4 months in, and I've been able to take great advantage of the vector databases and the patterns that we're going to be talking about, despite the fact that I do not have a deep background in machine learning. So I thought that might be interesting to folks here. I'm sure there's plenty of people on this call that know a lot more than I do. But in this talk, I want to cover what is a vector database. I like to do that first by saying, talking through what kinds of problems do the vector database actually solve for us? What kinds of applications can we build using a vector database that perhaps we couldn't have before, that was harder? And then the part that I'm most excited about is going to be some of the architectures and patterns and applications types that we can actually build using vector databases. So I will also do my best to leave some time for us all to do Q&A at the end. And then anything that I don't know off the top of my head, I'll be sure to bring back to the broader Pinecone team and make sure that we get your questions answered during a follow-up. So we're going to go through a technical exploration of what a vector database is and how AI applications think and the critical role that vector databases play in AI applications specifically. But first, I thought it'd be nice to kind of ground our discussion in a real world example. So in this slide, you can see 3 natural language ambiguous English user queries that you might expect to get in a given application. They might send it into the front end. And so we can see that just like, English is very ambiguous. It's famous for being ambiguous. There's the first query is, where is the Bank of England? So that's discussing a financial institution. Where's the grassy banks? That's like a landscape feature, like a hill. And then how does a plane bank or turn, gently while it's flying? And so in order to kind of ground our discussion about how vector databases and AI applications in particular work, I thought it would be interesting as a thought experiment. I'll first invite you to imagine that all we have is naive text-based keyword matching search. And we need to build an application that has to handle these 3 user queries and any other query that the user might send in. And so on our back end, you can imagine some code that receives the user's query, chops it up into distinct words and looks for the keywords, right? And then once it finds keywords, it crawls through the whole database that we have and returns any documents or rows where we might have the keyword bank. And so if you just kind of think and imagine, and perhaps we've all even built some of these systems before or used them in the past, what kind of performance or experience can we expect for our user if we're doing keyword searches on natural language queries that are ambiguous, where we're not controlling what the user can actually say? And we can imagine that, as we've all experienced, like that just keyword matching alone is not really going to provide excellent performance or a high quality experience for our end users, because we can't differentiate between a Bank of England, like a place that holds money, or a plane making a soft turn while it's flying. So in this talk, we're going to look at what a vector database is, but I like to, as I said, first understand what are the types of problems that they solve in particular. And so in order to do that, let's just take a step back and imagine, how does AI think? And when we're talking about thinking in the context of AI, what we're really talking about is this internal representation that the AI models have of the data that we're feeding them, or the data that they're trained on, or the data that they're looking at when they're servicing a user query, if you will. And so in order to understand AI, we can borrow some metaphors from what we know about human intelligence, right? And I'm sure you've all heard of neural networks. And so many different types of AI learn using neural networks, which are interconnected layers of neurons. And one way to think about those neurons or layers of neurons is a sort of stage of mathematical functions that have their own weights. And as we're feeding these neural networks immense amounts of data, they are continuously learning or being trained, and these functions are updating their internal weights or their parameters, if you will. And so what happens over time is, and here's like just a very simple diagram, but what happens over time is these functions continue to be exposed to more and more data as we're feeding them during our training period. They get to a point where they begin to extract high-level features. And the features are really features are, think about what makes the thing the essence of the thing. So if we're thinking about a cat, And eventually we train an image model to be able to say, that's a cat, right? Like what are the features that make up cat? So it could be like the soft fur, particular type of eyes, claws, the size in relation to other animals, et cetera. And so what's important to understand is that, eventually we as humans, even in today's world, come to feel that these AI models have an understanding of the data that they're being, presented with. And what's really important to understand for this talk and vector databases in general is that the internal representation of the AI model for these features is done with vectors or embeddings. So let's again ground this in a particular example. With apologies to anybody on the call who might have a fear of clowns, I promise there will be no jump scares whatsoever. But imagine that we are training a neural network on millions of images of clowns, and we want to eventually get to a point where our AI model can recognize this is a clown or this is not a clown. It can do discriminatory work in that fashion. So this first image is about, we see some clowns and they're playing in a park and they're doing different things, holding a balloon, pointing, maybe telling jokes. And then we continuously feed our neural network and model with more and more data and images of clowns. Perhaps we also see clowns performing tricks. They're performing at birthday parties. And eventually we get to a point where the AI model extracts the high level features from the data, right? It's seen so many clowns and it's updating its weights in the functional layers of the neural network, those neurons. And eventually it comes to determine that there are certain high level features which represent clownness. And importantly, these are things that even we as humans would agree represent clownness, if you will, or a clown, right? So it might be the very colorful uniform. It could be the frizzy hair wig. It could be a red balloon or the big floppy shoes, maybe the red nose. But we get to a sense of the same way that humans kind of think, okay, that is or is not a clown because of these things. The model extracts high-level features. And the way that the model represents those features internally is through vectors or embeddings. And so that begs the natural question, what are embeddings and vectors, right? So first, the important thing to know is that they're synonyms. They're the same things. We use them interchangeably when we're talking about them. And at a high level, this diagram demonstrates how you get embeddings. And so the technical definition is that embeddings are numerical representations that capture the essential features. And importantly, not just the features of the data, but the relationships between discrete objects, right? So, clown, large clown and small clown, they're related because they're both clowns, even though they're different. And so this can be words, documents, and it's represented in a continuous vector space. And we'll look at what that means a little bit more concretely in a second. But the really important thing to understand here is that we see, there's object 1, object 2, object 3. This is data in the abstract sense being sent into an embedding model. The embedding model extracts those features that it sees, and the way that it represents those features is via embeddings or vectors, which are lists of floating point numbers. And the really important thing to understand, and what's very cool about this, and what kind of represents sort of a paradigm shift away from traditional database modeling, if you will, is that this can be any type of data. It doesn't have to just be text. So we're also talking about images. We're talking about being able to do comparison search across image space. We're talking about audio, being able to match things and voices and people and discriminate that this is a noise of somebody dropping something and breaking a cup versus this is somebody singing a famous song. We can do it with video, etc. And so this becomes extremely powerful. But the other thing to note is that there are many different types of embedding models. You may already be familiar with some. One of the more popular ones, for example, is OpenAI's text embedding Ada-02. I'm sure a bunch of us have used it. There's open source and closed source embedding models, but at a high level, when we're talking about how we get embeddings, we feed data of any kind into an embedding model, and out come the vectors or the embeddings which represent those features and relationships. Let's try and visualize this a little bit more. So if we look into the high dimensional vector space, this is a visual representation of that. And imagine that this is like a Pinecone database that you've already stood up and you've stored a bunch of vectors in here. So when we talk about interacting with the database, we talk about upserting the vectors. That really just means inserting them, putting them in the database, such as Pinecones. And then the way that vector databases work at a high level is to group together vectors that are similar and have features that make them similar, and to group apart those vectors and pieces of data that are dissimilar from each other. And so here we can see in the high dimensional vector space that there's a representation in the database itself that these are not just names, they're not just phrases, right? You might have seen in a Western movie, this is Friday, so somebody names their horse Friday. It's not just a name. These are all days of the week, and they have that feature, and therefore they are grouped together more closely as neighbors in the high dimensional vector space, whereas these data points represented in blue could be a dog, this could be an airplane, this could be a mathematical function. They're dissimilar, and the vector database is representing that as well. So not just the features that make them unique, but also the relationships between them, and that is a function of how closely together they are represented in vector space or not closely together. So now that we've got this understanding of vectors and embeddings and why they're interesting, let's return to our original example where we were previously using naive keyword search matching, right? And now again, we can consider in the context of vectors, these same three natural language queries from our users, which are in ambiguous English, right? Where's the Bank of England? Again, talking about a place that stores money safely. Where's the grassy bank? A landscape feature that's further apart because they're dissimilar. The semantic meaning of the sentences is actually dissimilar. And then how does a plane bank or turn in flight is even more dissimilar from financial institutions. So they're spaced far apart. And this is really the essence of what gets to allowing us to build applications that seem incredibly intelligent and that are able to determine exactly what we're talking about and find highly relevant search results. So notice also at the bottom of the slide, now we have two new sentences. The first sentence is, the bees decided to have a mutiny against their queen. The second sentence, in completely different keywords and syntax, flying, stinging insects rebelled in opposition to the matriarch. These resulting vectors, after we pass them through the embedding model, are quite similar. They're almost identical in meaning. They are identical in meaning, but they use different words to convey that meaning. And so we would expect them to be very close together in vector space. And so this is to show that the power of vectorizing your data is that you can model the relationships at a very granular level, and in addition to the features that we talked about with the neural networks. So now that we understand why vectors are powerful, let's take a look at vector databases and how they work. So a vector database, loosely defined, is a database that allows us to manage embeddings at scale. And importantly, some vector databases, such as Pinecones, allow you to not only insert and update and delete vectors, but also update the index, which holds those vectors, instantaneously. So there's not, if you've worked as, again, folks that are even more familiar with ML and big data than I am on the call, if you've worked with architectures before where you need to wait because you're rebuilding the index, that's not an issue with the vector database. The performance is instantaneously updating the index, and there are certain places and use cases you can imagine where that's incredibly powerful, such as e-commerce, right? You might want to ensure that your users talking to your chatbot are able to get the latest products and that they're able to see the inventory immediately. So as you sell out of this famous Nike shoe, immediately the index is updated to say there's none left. If you add or do a new product launch, immediately that class of products is available within vector space for anything that's querying it to search it. So the other thing to understand that makes vector databases so powerful is that once your vectors are upserted and they're in this high dimensional vector space, you are able to query the vector database, and importantly, you give it a query vector. And so you say, and we'll talk about concretely what a query vector looks like, but you say, give me all of the nearest neighbors or the most similar vectors given my query vector. And then the database very quickly returns to you all of the nearest neighbors and the most similar based on those features we talked about that are represented in the list of numbers of the embeddings. And then finally, it's important to understand that some vector databases, Pinecone included, allow you to attach arbitrary metadata. If you're familiar with JavaScript, think of metadata as like an arbitrary object with any fields that you want to attach. And when you upsert your vector, which could be a chunk of text, it could be dialogue, you have the option of including whatever metadata you want. So let's imagine you're building a chatbot that is representing a television show character, and you want that chatbot to answer as if it is that character. Well, the metadata that you might associate with a vector, the vector could be, say, a plot summary of a given episode. In the metadata, you might want to say, this is the season number, this is the episode number, this is the runtime length of that episode, this is the author of that episode. And the point of metadata is so that when you query back the nearest vectors into your application, you can use that metadata however you wish in order to enrich your UX or your experience within the app for your end user. So metadata is the bridge from ambiguous language, as we've seen going into vectors, to structured data that you assign to your vectors. And then a quick mention of what about Pinecone in particular is interesting or different. It's a crowded market. There's, as you all have seen, there's tons of different vector databases. Companies that traditionally haven't been vector databases are creating and adding their own to open source projects, et cetera. So the thing about Pinecone that's unique is that we were designed from the ground up to be fully managed and run in the cloud. And so that means we run in AWS, we run in Google Cloud, we run in Azure, whichever cloud you prefer. But you don't need to worry about patching or security updates or, oh, there's this engine issue and I need to go upgrade my database, because our engineering team is handling that for you behind the scenes. You can create, manage, and scale indexes all through the API or the console if you prefer. You can even, I just saw a cool update where you can go in the console and in an existing index, you can just drag and drop a CSV file if you want and get your vectors in that way. And then we handle scalable ingestion. So we can handle hundreds of millions and even billions of vectors. And even when we're talking about billions of vectors, the amount of time it takes to query across that vector space and return you highly relevant results is sub 100 milliseconds. And so that's really important, because if you're building an AI application or generative AI application, like we're going to look at some examples in a second, you don't want your backend, especially your vector database, to add any noticeable latency or lag to your UI. And so you're able to get back highly relevant search results, even when you're dealing with hundreds of millions or billions of vectors in milliseconds, which is very important. And then finally, I'll just mention that, as I said before, I'm an application developer. I've used every type of this database that's represented here, as I'm sure you have. So there's key value stores like Redis, there's document stores like MongoDB, there's graph databases like Neo4j, et cetera. And then there's vector databases, and we feel that vector databases need to be purpose-built from the ground up, because they require specialized indexing, query optimizers, and also special storage in order to organize and retrieve data efficiently. It's not just about speed, it's also about ensuring that the relevance of what you get back when you query is extremely high. So with that out of the way, now we get to the part that I'm most excited about as an application developer. What can we actually build with vector databases, and what types of applications can we make that we weren't able to make before? So first, let's imagine, again, we've got the same query from a user, where is the Bank of England? And this architecture I'm showing you here is called semantic search, and it is sort of the foundational architecture that you're going to see repeated again and again in more advanced applications and architecture. So, once we understand this part, you can pretty much go anywhere with vector databases that you want. And essentially, semantic search is the way that we ensure that we're always returning accurate results for those same ambiguous user queries we looked at in the beginning. So unlike naive keyword matching, what semantic search does is takes the user's query here, converts it into a vector by going through the same embedding model that we actually put our content or our data in. What comes out is the query vector. So this is just like with our content. This is a vector that has features that are represented as floating point numbers in an array, and we send that through the Pinecone API, and we ask the vector database, search all of vector space and find me the top 3 or the top 5, whatever you want, top 1,000 nearest neighbors, and return those in the query to me. And this is incredibly powerful, as we'll see in a second. But again, you can attach whatever metadata you want during that upsert call. And that's what we're seeing here in the vector database, where we've got metadata attached to each vector. So you're not just getting back your vectors that are the nearest neighbors, you're also getting back whatever arbitrary metadata you defined. And now these highly relevant results are going back to the application. You can imagine that your application has an API key, and it's perhaps querying or calling ChatGPT and OpenAI. And now it has the highly relevant query results that match the user's actual semantic meaning. And this is what is the foundational shift here. Like, we are actually looking at what the user means at a semantic level when they query our system with a semantic search architecture. And that's what's enabled by a vector database such as Pinecone. And this is what allows us to build the really intelligent AI chatbots that you've seen. Let's now look at this in the context of, this is a very hot topic. We see lots and lots of interest in this right now. So LLMs, or large language models, as you're aware, such as ChatGPT, suffer from a problem called hallucinations. So let's just take a quick detour and also understand how that same architecture we just looked at can solve this really thorny problem of LLM hallucination and what it means. So LLMs like ChatGPT, for example, and specifically, if you've ever used it, you know that eventually it'll say something to you like, I'm an AI language model. I don't know about current events because my training cutoff date was September of 2021. So therefore, anything that's happened since then, I haven't been able to see it. I don't know, right? And eventually OpenAI needed to kind of define a cutoff point, whether it was either because of the cost of training or they wanted to get the model out to the market. But these are the same problems that everybody building foundational models, as we call like ChatGPT, are going to face. And so eventually you need to pick, like, this is the end of the data. This is all the data we scrape from the internet. These are all the books we want to feed it. This is all the conversation, and we need to stop. And so if you just query the base LLM, if you just query ChatGPT's model alone and say, how many customers do we have in New York City? You might get a response back that says New York City has 88.4 million potential customers as of 2021. What's interesting about that response is grammatically, it's perfect. Syntactically, it seems sound. It's unfortunately factually completely incorrect and a fabrication, because New York has 8.5 million people living in it. So there can't be almost 10x that number of potential customers. The worst thing about this, and the sneakiest part of it, is because of the LLMs are built and designed from the ground up, they do not understand that they are hallucinating. And so they will give you back this answer very happily and let you run with it. And now let's examine why in the real world, if you're actually producing non-trivial applications with generative AI or exposing chatbots for support even, that can really become a thorny issue. And it can actually cause not just brand damage to your company, but it can also potentially cause harm in the real world. So let's imagine a different scenario now. We have a user who has purchased a Volvo car, and they're on the Volvo support website that maybe has a chatbot. And their question is, how do I turn off the automatic reverse braking on this particular Volvo, the Volvo XC60, right? If we send that query directly to the generative AI model, just like typing into ChatGPT and chat.openai.com, it might come back with something that says, it looks completely grammatically correct. It looks syntactically plausible again. And it's leading this user down a complete rabbit hole because it's hallucinating, right? So everything it says seems reasonable. Press the settings button, go to driver assistance settings, select park assist, look for the option to turn off automatic braking. But unfortunately, because the foundation model of ChatGPT has never been trained on Volvo's actual user model, user manuals, right? Or any of its actual instructions for vehicles, it's literally fabricating this out of thin air based off of what sounds linguistically most correct. And so that, again, we get a plausible sounding but total hallucination, which in the context of trying to turn off a safety feature in your car could actually cause real world harm or be dangerous. So let's now look at a architecture or pattern that we're seeing a tremendous amount of interest in. You may have also seen this on the internet already. It's called Retrieval Augmented Generation. The acronym is RAG. And the reason that this is really interesting is it's not the only way to fix the hallucinations problem, but in our opinion, it's the most cost-effective way, and it's also the most reasonable and tenable way, because as I shared in the beginning of the call, my background is in application development, and I'm an infrastructure automation person. So I don't have ML training, but I am very comfortable with programming languages, front end, back end, and learning to use code. And so, for example, I took a 3-week break before I started at Pinecone a couple months ago, and I built an AI bot that was impersonating Michael Scott from the television show The Office using Retrieval Augmented Generation. And after looking at an example, I was able to implement that myself in Python and JavaScript without much trouble. And so this is really powerful because companies tend to have more application developer expertise than necessarily machine learning and data science expertise. That certainly helps. But the reason why Retrieval Augmented Generation is powerful is that you can have your application developers help you with it, essentially. So in Retrieval Augmented Generation, let's look at the architecture. There's really 2 phases. The first phase, this would be us as developers, engineers, machine learning experts working together, preparing our data store or our database before launching a chatbot, for example. And so we want to train this, we want to create a contextually specific database to contain all of the information from our company. So we might read URLs from our own documentation. We might read our API documentation. We might have PDFs full of our service offerings, manuals that explain how different products actually work. And we can read all those URLs in code. We can chunk them into documents, which is just a pattern of making them a little bit smaller, pass them to the embedding model. And just as before, we get out vector embeddings, right? We get out the list of features as floating point numbers. We can optionally attach metadata. We could say this is for the product like this, the shoe is orange, the price is $99, whatever we want. And then that goes through the API. And at the end, we have a fully populated vector database that contains context-specific information about our company, our proprietary data, what we're actually doing, the subject matter. So when I built this for myself for fun, this vector database that I used was completely populated with human written summaries of every episode in The Office. And so then my chatbot is able to refer to that. And the way that the chatbot or generative AI application is able to refer to this is defined in this second phase, or this RAG architecture here. And if you're paying attention, you'll notice that this is quite similar to semantic search, and that's because it uses semantic search under the hood, right? So the essence is the same, but the results are pretty game-changing. So again, the user asks an ambiguous natural language question. We convert that into a query vector. It goes through the Pinecone API. But now what Pinecone's database is returning is the actual results that we trained the database on for our use case. So it could be, all kinds of facts about the Bank of England, how much money it has on hand in a given day, its history, where it was founded. Like if we were just making a bot that wanted to be an expert on the Bank of England, we would have populated this database with all of those documents, which means whenever a user asks a question to our end application or our chatbot or AI application, we are actually looking at their semantic meaning, and we are returning our own documents that are the most semantically similar to what they asked us about. And this is incredibly powerful. Let's look at this in the context now, that same example with retrieval augmented generation. The user's asking, how do I turn off automatic reverse braking on this Volvo XC60? So the big idea is that the large language model at the center needs access to a data store of context and real world facts. So imagine now that we're working as engineers and data science experts at Volvo. We could take all of the Volvo users manuals, we could convert them to whatever format, Markdown or PDF. They go through the embedding model. They come out as embeddings and vectors, as we've seen. They go into the vector database. Now this vector database is absolutely replete with factual information about how every model in the Volvo lineup actually works, how you actually interact with its different features, how you turn settings on and off, what the specs are for the car, et cetera. And you can imagine here, the metadata that we attach to our vectors as we're upserting them might be make, model, year, color, whether or not it's electric vehicle, true or false, right? These types of things. It's whatever you want to define. So now the world looks, with just a couple of differences in the query path, looks quite different for this user, because our user asked the exact same question: how do I turn off automatic reverse braking on the Volvo XC60? We put their query and the application code, whatever our backend language is, through the same embedding model. We get out the query vector as we've seen before. That query vector now goes to the same vector database that we've made into this repository of Volvo user manuals. And what comes out finally for the LLM, whether it's ChatGPT-4 or any other, is not just the user's query, but also in natural language, but also the context. So if they are asking about the Volvo XC60 and they're asking about reverse braking, this context is going to include, this user is asking about Volvo XC60, here's all of the manuals, or here's all the documents about Volvo XC60 and automatic reverse braking. So now, ChatGPT, with all of this information, please answer this user's question. And this is where the game changes completely in terms of relevance and quality of response, because now the LLM is able to look at factual data. It's still smart enough to answer the user's question, but it's actually grounded in the truth that we've added to the vector database. So the driver can choose to deactivate auto brake with rear auto brake and cross traffic alert. The warning signal can be deactivated separately. activate or deactivate the auto brake with this button in parking camera view. So this is the factual answer. It's completely different from the previous hallucination. And this retrieval augmented generation pattern or architecture has allowed us to fix the problem of hallucinations in LLMs within our generative AI application. That is what makes it so powerful. So getting up to time here, I want to leave some time for questions. I want to make it clear that generative AI is exploding, as we all know. It's super exciting. There's definitely a tremendous amount of awesome things that you can build that are a lot of fun, that are making money, that there's tremendous forecasts of just generative AI alone, what it can do for businesses. But that's a small part of what vector databases enable, right? And so as I mentioned before, vector databases also enable semantic and similarity search, as we saw, not just for text, but also images, audio, video, objects within video frames. We saw how a vector database can help ground chatbots and support bots in proprietary or context-specific data that you might have for your company. We saw how it fixes hallucinations via retrieval augmented generation, and then that's just a few potential use cases. I can also share with you that if anyone's interested, I'll share it later in this call, or I can screen share and show you. We've got tons of Jupyter Notebook examples in GitHub that demonstrate how to do different patterns, all using a vector database, and you'd be surprised at the range of applications represented by those Jupyter Notebooks. And then we also have, for the TypeScript folks and for JavaScript developers and application developers on the call, we've got Vercel templates that implement retrieval augmented generation, that are easy to launch, and that demonstrate RAG from a code perspective. But again, this is just a small piece of what you can actually do with vector databases. The true power is being able to get at the semantic actual meaning of what a user's query is, and then find them the most similar results. And the level of relevance you can achieve doing that using a vector database at scale is pretty phenomenal. And that's what enables these hyper intelligent or super smart chatbot experiences that we're all kind of starting to see crop up now. All right, and with that, I will close by saying thank you all so much for your time and attention. Thank you all for being here with me today and allowing me to come and speak with you. Really appreciate it. I hope this was useful for you. Feedback is also welcome about how we could make this better for you in the future. And I will now also open it up to any questions. And if it's not something I know off the top of my head, then this is being recorded and transcribed, and I promise that I will go back to the broader Pinecone team and make sure that we get your question answered in a timely fashion. All right, thanks so much. Yeah, and looks like Venkatesh, if I'm saying that correctly, you've got your hand raised.
Yep.
Go for it.
Yep. Hey, Zach. Okay. So I can see like the primary advantage of using the RAG architecture with the vector database would be we don't need to retrain our large language model, right?
That's
like
correct.
I can still use my same base model, whatever, like Bird, GPT, Llama 2, whatever we
Yep.
have. But what is there like a limit to what extent like can we survive without going back to like fixing or like retraining my original my base LLM and just using the vector database?
Yeah.
Is there a limit to that, or like it is able to handle anything?
Yeah, that's a really excellent question. I thought about I should probably have included a slide there to show, and we have slides in other presentations about. I want to make it clear that, as you pointed out correctly, like RAG is not the only way. You could go back to your base model, as you're saying, and fine tune it for a different example. But even that requires, ML expertise and data scientists that you may or may not have on staff. And then RAG just happens to be what we find to be the most cost-effective way, because it's also quick to implement from an application level. So to answer your question about when does it start to kind of show its wear and tear, from a scale perspective with Pinecone, that's not really an issue because, again, we can handle hundreds of millions or billions of vectors very quickly. I think it is an interesting question. I don't know the answer myself perfectly yet about where we're going to see this go. There's been lots of discussion on social media. You've probably seen it where some people are claiming, hey, RAG is a hack, right? It's really addressing the fact that, the context window for these LLMs is limited. And so at what point do the open AIs of the world and other models and open source that's catching up so fast, or maybe in some ways leading the way, fix their context windows and make it so that RAG becomes less and less useful? That's entirely possible. I mean, as you all know, it's like the entire space is changing so quickly. The other thing I'll mention is that normally when we have the slide that talks about here are your options in terms of like difficulty and speed to fix hallucinations, the first is also prompt engineering, right? You can get so far with prompt engineering, and you can say, hey, in the future, don't say that weird thing you said. And then if you need, this, then please browse the internet for the user, et cetera. But as we also see on Hacker News every day, prompt engineering is not perfectly reliable. You can jailbreak LLMs super easily by just asking it questions. Even the latest, I was playing with the latest LLM, like DALL-E 3 integration for OpenAI, and it's incredible. It's super fun. But if you put certain text in an image, it'll just do what you ask it to and drop the whole prompt, right? So it's like not even prompt engineering is perfect, and it'll only get you so far. And it also can't help with dynamic like context injection. So imagine it's like you've got the entire library of like classical literature in your Pinecone database or some other vector database. RAG is still going to be more effective at actually finding the exact results the user is asking for and then immediately returning them. But you raise an excellent question about like, how long is this going to be the case? I don't personally know. Will it always be needed? I also don't know that. I just know that right now it works pretty well, and that I can actually say from personal experience, having implemented it. And in terms of the actual scale on the back end, there doesn't appear to be any meaningful limit yet that I've seen in terms of just the vector side of things.
Okay, because I think having like that limit or an understanding of what the limitations are would at least prompt like any organization to say, okay, hey, we are reaching this limit. Maybe it's now time to fine tune my underlying model. I cannot just rely on my RAG anymore.
That's an excellent point. Yes, thank you. And I will I think I'll update the slide now with that in the future, because you're absolutely correct. There are certain times and places where RAG might be appropriate. Like if you're doing a chatbot or support bot, it's excellent, right? It's super quick. You could have an application developer fix it in 2 days, and there you go. But then when you're really dealing with high scale or very specific use cases where you're trying to do something that only your company knows, like maybe fine tune, and you also have the expertise on staff, perhaps fine tuning is better. It just takes longer, and there's a cost to it for sure. And then of course you can go as far as saying we're going to build our own foundational model, like ChatGPT, right. But then it's also that's also cost prohibitive for most organizations, right? I think Sam Altman of OpenAI shared that training ChatGPT, they estimated it was like over 100 million in just compute costs alone before you.
Right. Yeah. I mean, there aren't that many. Like at least in finance, there's like Bloomberg GPT. Again, like really big organizations with a lot of funding can afford to do those.
Yeah.
But a number of other organizations, and in terms of like cost, right? Like is there like if I'm comparing, okay, designing this vector database and using that versus like fine tuning, is there like a cost comparison we can say on like either building this vector database up plus ongoing cost to maintain it versus like fine tuning on a regular basis? Do you have any idea of in terms of like cost estimate for that?
That is an excellent question. I can tell you that internally, I think I can share this, that internally we're working on some tooling to make it easier to understand what your cost would be. We're also looking at some tooling that might help you explore or play around with different scenarios and approaches that do or don't use the vector DB and do or don't use certain models even. I think that's a great question. I think it also comes down to, again, like if your team is replete, if you've got deep data science expertise, which I don't personally have, then it's like, hey, fine tuning is not that scary, and we can handle it this way. But I can also share that even at high scale, for certain organizations, there's a sweet spot where even Pinecone level performance is very affordable. So, but I don't have those figures for you yet. I think there's also a data sheet that one of my colleagues just put together. And if that contains any of that information, I will also make sure to get that to you, because I think that might be helpful. I think it goes into comparisons around like how fast we are on average and like what scale we're actually talking about when you're dealing with certain use cases. So
okay, and sorry, one last question.
No, please. These are excellent questions.
So in terms of like embeddings, like the embedding dimensions, like I'm guessing that's user defined, right? Like, we can define
Yes,
what dimension it
you
can be
can.
used based on my base model.
Correct. Absolutely. When you create in the API call, we've got Python client. So I'm a developer advocate, but the other half of my job is open source maintenance, and so I work on the Python client and like the TypeScript client, et cetera, along with my colleagues. When you make the API call to create an index at Pinecone, one of the parameters is dimensions, and so you can define like 1536 if you're using OpenAI's text embedding ADA, whatever your base model requires, you can specify that when creating your index.
Okay.
Yeah.
Thank you so much.
Of course. Excellent questions. Thank you. Any other questions I can help out with? And then I made a mental note that I'm going to get the data sheet for you folks and send that around if that's interesting. And then also ask about how we can, if we already have a cost calculator, and if not, how soon that might be coming up.
Any questions from the audience?
And also, by the way, even if you think of something later, I'll type my email in here. So it's
Yes.
Zack.p@pinecone.io, and I am always happy to answer field questions. You can also find me, I'll put this on here, you can find me on LinkedIn here. And like I said, anything that I don't know, I'll take it back to engineering or sales or whoever's the right folks to ask. If you have questions about the open source stuff, by the way, I do work on that. So maybe I'll just quickly share this with you folks, because I think we do a really good job of maintaining these. And there's a tremendous amount of work. Like my colleague James, for example, you might have seen his YouTube videos. Like he's definitely a rock star. And all of these notebooks here, we've now added like some. I have a video about how to use it, and there's a guide about how you can run them for free in Google Colab. So please feel free. These are open source, so as you can see, like you don't need to be logged in. You don't need to be a Pinecone customer. We even have a free tier, which before I joined Pinecone, I was using, and that free tier lets you use one index, and you can really use it. Like I put a production chatbot and deployed it using that, and so we go into all the different use cases here, like chatbots, Nemo guardrails. This is super interesting. This is something James just figured out, where NVIDIA released this framework for putting guardrails on those LLMs that we just talked about, where if you can say like, don't answer questions about politics and don't be offensive, right? You can actually start defining some of that stuff in here. And then all of our examples, if you click open in Colab, it's free to run these in Google Colab. And all you would need is to go get your API key from Pinecone, which is also free. OpenAI, I think, is free unless you want faster performance, then you got to pay for it, right? It's $20 a month. But just to say that these exist. So if any of you are kind of open source or data science or Jupyter notebook hackers, check out this link as well. And I'll drop that in the chat too, so anyone can copy it. And then if you have questions about this is kind of my responsibility too. So happy to answer questions, fix bugs, feel free to open issues if you have any questions. But yeah, otherwise, I just want to say thank you so much for your time and attention. I really appreciate it. This was a lot of fun for me. So I hope it was useful for all of you guys.